This lesson deals with Supplemental Problem 318. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems, starting on page 25. Let's revisit the cigarette lighter adapter for the Sony Discman CD player that we did in Chapter 2 on pages 76 and 77. But this time let's use a transistor regulator, where I've got an NPN transistor, a Zener diode, a resistor, our car battery, and then our CD player. I'm going to use a power transistor, a 2N3055, which has a VB on around 1 volt, a VCE sat around half a volt, and a beta F around 50. For this Zener diode, the 1N5229, it's a half watt Zener with a Zener voltage of 4.3 at 20 milliamps. Suppose the battery voltage is 12 volts, and we use the value of R sub L we used in Chapter 2 of 13.2 and 6.6. We'll do the 13.2 first. Assume Q1 is active and that the Zener current, as shown, is greater than 0. Then solve for I sub B, I sub Z, and V0, and then verify the states that we've assumed. Then what power is dissipated in the resistor R1, the Zener diode D1, the load R sub L, the CD player, and the transistor Q1 if the power dissipated is roughly the collector current times the collector emitter voltage. Then repeat all this again for the case of 6.6 ohms. These were calculated based on currents that were drawn by the CD player under different conditions. And then lastly, suppose that R sub L is an open circuit. In other words, it approaches infinity. What's the state of Q1 and how much power is dissipated in the Zener diode? Let's put the model in for our transistor and Zener diode. We had a 12 volt battery. We had a CD player from here to ground, and we had a 120 ohm resistor. The base, collector, and emitter were hooked up here. And then we're assuming the active region, so between the base and emitter I have VBE on, and then between the collector and emitter I have a current source of beta FIB. And then we assume that the Zener was in the Zener region. Zener voltage was 4.3, and this was the current I sub Z. The output voltage here, if we go around the loop, rise in voltage equals -1 plus 4.3 or 3.3. Same voltage we had in our Chapter 2 notes. The current in the CD player I out is going to be I sub B plus 50 I sub B, 51 I sub B. But that's also V out over R sub L, which is 3.3 volts divided by 13.2, and that's 250 milliamps. Then now I can solve for the base current. The base current times 51 is 250 milli. Divided by 51, I get I sub B, and that's 4.9 milliamps. And that's greater than or equal to 0, so that's one of our checks. The current that's flowing in this 120 ohm resistor is going to be the voltage across it divided by the resistance. This node voltage is 12, this node voltage is 4.3. The difference of those divided by 120 ohms is 64.17 milliamps. Current in the Zener is going to be current that enters the node, which is I sub R1, and minus I sub B. I sub R1 is 64.7 milli, and I sub B was 4.9 milli. That gives me 59.27 milli. And that's greater than or equal to 0. The guess for the Zener is also correct. We last need to check the collector emitter voltage and make sure that's greater than the saturation voltage. That's the difference of two node voltages. This node voltage is 12 volts, and this node voltage is 3.3. Difference of those two is 8.7, and that is greater than or equal to the saturation voltage of a half, so the states are verified. One of the things we saw in the Chapter 2 notes was that we had a very high wattage resistor in our regulator. Let's see what the wattage of these components are. Power dissipated in the resistor R1, you can calculate a lot of different ways. I'll do I squared R since I know the current through it is 64.17 milliamps, so square that times the resistance of 120 is about half a watt or 494 milliwatts. The Zener diode has got 4.3 volts across it, and we found that the current was 59.27 milliamps, and that's 255 milliwatts. Power going to the CD player is V out times I out, 3.3 volts times 250 milliamps. That's 825 milliwatts. And lastly, the power in the transistor is approximately the collector emitter voltage times the collector current. You could also add in the drop across the base emitter and the base current, but most of the number is right here. I've got 8.7 volts across the collector emitter, and then my collector current is 50 times the base current, and that's 2.13 watts. Let's repeat the previous analysis with a 6.6 ohm load. This is a case where we're drawing 500 milliamps and 3.3 volts across the load. The output voltage is still a difference of two voltages, and it's still 3.3 volts. The output current is 51 I sub B, but now the load is 6.6 ohms, and so that gives 500 milliamps, and dividing that by 51, I get 9.8 milliamps. So that's a little bit higher, but it does check it's positive. The current in the resistor is still the difference of the two node voltages, 12 and 4.3, divided by 120, so that stays the same. The current in the zener is the difference of R1 and I sub B, but I sub B has gone up a little bit. The difference now is 54.37 milliamps. It's a little bit lower. The collector emitter voltage is still 12 minus 3.3, 8.7, half a volt, greater than or equal to the saturation voltage. Our states are verified. You can take a look at the power dissipated in our components. For the resistor R1, it's I squared R. You have the same current and the same resistance, so we get the same power dissipated. Now in the class notes in Chapter 2 on pages 76 to 77, this was 8.9 watts. So we've reduced the value dramatically by not having the current go through the resistor that's also going into the load. We just have that current going into the zener, into the base. The power dissipated in the zener is V sub Z times I sub Z, so still 4.3, but now it's 54.37 milliamps. And that's 234 milliwatts. And in our class notes in Chapter 2, this was 1.92 watts. So again, we dramatically reduced this for the same reasons. The power out is now 3.3 times half an amp, that's 1.65 watts. And the power dissipated in the transistor is again approximately VCE times I sub C, so that's 8.7, and then 50 times the larger value of base current, and I get 4.26 watts. Now, what would happen if we were to shut off the CD player? Well, the emitter current would go to 0, and that would imply that the base and the collector current also goes to 0. I can't calculate the base emitter drop because I've got an open circuit here, but I could calculate the voltage across the base collector. I got 12 volts here and 4.3 here. It means I've got 7.7 here. From the base to the collector, I've got a minus 7.7, so I'm definitely in cutoff. The current in this resistor is going to be the same as it was before. It's the 7.7 volts divided by 120, or 64.17 milliamps. Now the base current is 0, so all that current goes into the zener. The zener gets 64.17 milliamps. That's the most it's ever going to get. And the power dissipated then goes up to 276 milliwatts. And this is, of course, below our rated value of 500 milliwatts for that zener diode. Our design should work. And this is supplemental problem 318.